new international airport at Kuala Lumpur was to be constructed with a runway 11,400 feet long and a load classification value of 100. This would be able to take any aircraft in current use and in the foreseeable future. When construction started, topsoil was first stripped to a depth of 12 inches and stockpiled. The volume of cut and fill for the main earthworks was about 5.5 million cubic yards, but because of the increased density of the soil after compaction, a total of about 6.75 million cubic yards was excavated. The fill was compacted to formation level to an average dry density of 95% British Standard heavy compaction. A concrete curb was placed on each side of the pavement to provide a working and reference level for the pavement. A soil profile of the site shows weathered granite and alluvial deposits. Cutting through a granite hill exposed 3 soils of distinctive color and texture. Type 1, in the top 15 feet, was used for fill under pavements. Type 2, between 5 and 30 feet, was used in the lime stabilization, and Type 3, from below 17 feet, was used for fill under turfed areas. Site investigations and laboratory tests had indicated a subgrade CBR of 10%. This meant that a construction thickness of 20 inches was needed to take the design loading. The construction was made up as follows. First, a sub-base of 4 inches of lime-stabilized soil was laid on the formation. This was needed because the base could not be compacted well enough on untreated soil. Next, a 12-inch bitumen-bound base was laid in 3 4-inch layers. This material was chosen to reduce delays due to bad weather, which can seriously affect conventional construction, and to enable stocks of waste sand from local tin mines to be used. The asphalt surfacing was applied in 2 layers, a 2.5-inch binder course and a 1.5-inch wearing course, totaling 4 inches. Crushing strength tests carried out in the laboratory showed that 4% of lime was needed for the sub-base. The technique of the test is shown here. First, a representative specimen is riffled out from a bulk sample taken from the site. Calculated quantities of lime and water are added to the soil. After mixing, the correct amount of material is weighed and compacted into a mold of known volume. A cylindrical specimen of the required density and moisture content is produced, in this case 95% of British Standard heavy compaction at optimum moisture content. The specimen is sealed with paraffin wax and allowed to cure for 7 days. After curing, the specimen is stripped of wax. It's placed in a compression testing machine and loaded at a controlled rate. The maximum load attained is recorded and the compressive strength calculated. The contractor decided to make his own lime, bringing limestone from a quarry 25 miles away and using felled rubber trees as fuel. 6 11-foot diameter brick-lined kilns, 14 foot deep, were constructed on a steeply sloping site, giving access to the top for loading and to the bottom for fueling and removal of lime. The burning was carried out in the traditional Chinese manner. A dome is made with limestone blocks at the bottom of the kiln, then more blocks are placed by hand over the dome with smaller pieces towards the top. The hearth is filled with wood to a depth of 4 to 6 feet. It is then partially bricked up, leaving holes for ventilation and refueling. The kiln is fired and stoked for 72 hours. It's then allowed to cool for a further 48 hours with the ventilation holes closed. The entrance is knocked down and the ash covered with metal sheets. Within a few hours, the burnt lime slakes in the moist air and collapses. The lime is then put into a large shed where air slaking continues until a fine powder is produced. It's then picked up in a suction hose, passed through a cyclone extractor, and material larger than 150 microns is removed. One such kiln produces about 30 tons of lime per burning and needs about 60 tons of wood. One kiln can be fired every 8 days. Because rain often made mixing difficult, a shed 35 feet wide and 600 feet long was constructed where the materials could be mixed under cover. In dry weather, the shed was filled with soil to a depth of 2 foot 6 inches and the top 6 inches pulverized. Lime was spread over the soil and mixed by the pulvimixer when it was impractical to operate in the open. As soon as the formation dried sufficiently, this layer would be stripped out and transported to the site. Occasionally water was added to the soil-lime mixture to bring it to the correct moisture content during mixing. With experience, it was found that the pulverization of the soil was improved by spreading the lime after only one pass of the pulvimixer. The lime and soil were mixed together in another pass, and after a delay of several minutes, pulverization was continued until 80% of the mix was smaller than 3/16 of an inch. The mixed stabilized soil was excavated by traxcavator and loaded onto dumpers. It was then tipped into a spreader and deposited in layers calculated to give a 4-inch compacted thickness. After spreading and grading, the stabilized soil mixture was given initial compaction with a few passes of a 2.5-ton smooth-wheeled roller and 10 passes of an 8-ton smooth-wheeled roller. This was followed by at least 7 passes of a 2.5-ton towed vibrating roller, which increased the density to 95% relative compaction. After compaction, the dry density of both the formation and the layers of stabilized soil was checked by the sand replacement method. The moisture content was checked with a speedy moisture tester. The readings were occasionally checked by the oven drying method. After the stabilized soil had cured for 7 days under a prime coat of cut-back bitumen, the bitumen-bound base was constructed. The material was mixed using a Barber green mixing plant. The aggregate was made up with 40% crushed granite of 1.5-inch nominal size, with sand waste from local tin mines and 2% filler. A bitumen content of 3.3% was added to give a Marshall stability of at least 650 pounds. A Barber green spreader was used to deposit the 3 4-inch thick layers of the base material. The temperature was controlled throughout the operation. The materials were mixed at 315 degrees Fahrenheit and laid at about 280 degrees Fahrenheit. A variety of steel-wheeled and pneumatic-tired rollers was used to compact the base. The construction was completed with a 2-layer surfacing comprising a 2.5-inch layer with 4.2% bitumen and a 1.5-inch layer with 5.4%. The maximum stone sizes were 1.5-inch and 3/4 of an inch, respectively. The stabilized soil subbase provided a useful working platform. Also, using a dense material of low permeability, advantage could be taken of the relatively low moisture content and strong condition which existed in the subgrade. The choice of a bitumen-bound base enabled a low-cost local material to be used and therefore saved on the quantities of material requiring crushing. It also enabled a fairly tight time schedule to be maintained in spite of a very wet climate.